Assalamualaikum and hi, we are from group 13 and our topic for this presentation is gas-filled dosimeter. We have 4 members in our team, Isa, Wu Bekai, Camila and me, Amira. This is the overview for our content, starting from the introduction, then the working principle of the gas-filled dosimeter, its dosimetric properties, application, advantages and disadvantages, and lastly, why and when gas-filled dosimeter is preferred.
For the introduction, a dosimetric system is an instrument that measures dose of ionizing radiation. It can be classified as active and passive dosimeter. Active dosimeter can display the dose value directly, while passive dosimeter cannot display the dose value directly, but it can record a signal which must be retrieved and converted to dose by a reading device. In gas-filled dosimetric system, it consists of dosimeter, which is the gas-filled chamber itself, and the electrometer to measure the electrical current generated by the ionization process. They are referred as gas detectors because the signal is produced when charged particles ionize the gas in the detection chamber. There are many types of gas-filled dosimeters such as ionization chamber, proportional counters, and gigamolar counters.
Gas-filled dosimeters are devices used to measure the amount of radiation. They function by using a sealed chamber filled with a specific gas, such as helium, neon, or nitrogen. When these gases are ionized by radiation, an electron current is produced. Deposit slight difference in their operating method. All these dosimeters are based on the same fundamental principle. In a gas-filled dosimeter, the basic components include a gas-filled chamber, electrodes, and a high-voltage source. The high-voltage source creates an electron field between the electrons. When radiation passes through the chamber, the gas is ionized and the electrons collect the resulting ions, thereby forming a current. Those measurement is achieved by measuring the current produced during the ionization process. Therefore, by measuring the current, we can accurately detect the radiation. This slide shows a detailed illustration of the inside of the dosimeter. We can see the anodes and the cathode as well as the emitter used to measure the current. Each component is indispensable in the process of the dose measurement. In this slide, we have specific steps from radiation exposure to the measurement of change in conductive. This series of steps from the operating cycle of the dosimeter, ensuring the accuracy of its measurement.
Hi, Assalamualaikum. My name is Camila binti Burhanuddin. So next I will explain about dosimetric properties. So the first one is accuracy and precision. When it comes to measurements, the uncertainty can be occurred. So uncertainty means that the doubt that exists about the result of any measurements, and this uncertainty is related to the measurement quality that can be taken, predictability and repeatability. This is often expressed in terms of accuracy and precision. So what is accuracy and precision? Accuracy means that the dosimeter can measure the measured quantity of their expectation value that is near to the true value. While for the precisions, the measurement can be reproduced under similar conditions, and the data that we get can be approximately obtained in a repeated measurements. Thus, gas field dosimeters are precise and accurate reading, as it is predictable and well understood through different energies and types of radiations. Second, the dose rate dependence. As we know, an ideal dosimeter should be independent of the dose rate so that it can provide accurate measurement no matter the rate of radiation exposure. Independence of the dose rate also, it can ensure that the measurement reflects the actual absorbed dose regardless of how quickly and slowly the dose is delivered. However, the gas field detectors depend on the dose rate, so they can produce a nonlinear behavior at very high dose rate. Okay, third, linearity. As we can see from the graph here, the higher the dose, so the dosimeter reading also increasing. So it means that the dosimeter reading should be linearly proportional to the dosimetric quantity. However, sometimes a non-linearity can happen. As we can see from the graph A show that the beginning it exhibits linearity with the dose, and then it will become supralinear, which makes it above the linear line, and then finally it will become saturated. For the graph B, it exhibits linearity also at the beginning, and then it will become saturation at high dose. The gas field dosimeters always show linear response to the different levels of radiation dose. This is due to the nature of ionization process within the gas. Inside the gas field detectors, the incident radiation ionizes the gas atoms, producing electron-ion pairs. This ion pairs form is directly proportional to the energy deposited by the radiations. Since its response is proportional to the energy deposited, the relationship between the detected signal and radiation dose remains linear over a wide range of dose levels. Fourth, energy dependence. The radiation's energy spectrum can affect how gas field dosimeters react. The amount of ionization in the gas can vary depending on the kind of ionizing radiation, which can affect how the dosage is measured. So to make it simple, the detector's response varies with the energy of incident radiations. Fifth, sensitivity. Gas field detectors are sensitive to ionizing radiation. It means that they can detect low level of exposure. Example like ionization chambers, it can detect very low of X-rays and gamma rays, which is less than 1%. 6. Readout convenience. Gas field detectors have a direct reading measurement, so it is more convenient than passive dosimeters such as films. Thus, we can get the reading as fast as possible after exposure without the need for other instruments to read out the reading. Last but not least, convenience of use. Gas field detectors are reusable, means that it can be used again and again, and also their sensitivity does not change during the course of their life.
My name is Nur Ezal, and I will be continue with the application for gas field detector. So there are three applications for gas field detector, which are giga mula, ionization chamber and also proportional counter. For gigamolar and proportional counter, they operate in pulse mode, and meanwhile ionization chamber, it operates in either current mode or pulse mode. Briefly, gigacounter consists of gigamolar tube which has the sensing element that detects radiation and the processing electronics which display the results. Gigacounter detect alpha, beta, neutron and gamma ray using ionization effect produced in the GM tube. For detection of alpha, beta and gamma, there are two main types of gigatube construction, namely N-window and windowless type. Alpha and beta particles can only be detected by a thin window. Hence, this N-window must be thin enough for alpha and beta particles to penetrate. Windowless type allows high energy beta particle to pass through. As the name suggests, this tube has no window and has more stopping power. Other than that, for detection of neutron are neutral particles and subject to strong nuclear forces. Therefore, neutrons are not directly ionizing and usually have to be converted into charged particles before they can be detected. Gigacounter that detects neutron must have the inside of tube coated with boron. The next application is ionization chamber. Ionization chamber are the simplest of all gas field detectors. Their normal operation is based on the collection of charge created by the interaction of radiation in the gas, and this is a type of absolute dosimeter. Ionization chamber can be used to detect alpha and beta particles using thin N window. Same as gigacounter, the thin window of IC must be thin enough for alpha and beta particles to penetrate. For gamma detection, IC utilizes windowless tube since gamma is less penetrable the metal wall of the chamber. Ionization chamber have a uniform response to radiation over a wide range of energies and are the preferred means of measuring high levels of gamma radiation. For neutron detection, since neutrons are neutral, it must be converted into charged particle before can be detected. The inner surface of ionization chamber must be coated with tin of boron, same as gigacounter. Proportional counters is the detection and measurement of ionizing radiation through the use of an electric field. It utilizes the phenomenon of gas multiplication to increase the pulse size by factors of hundreds and thousands. For detection of alpha, beta and gamma, proportional counter enable discrimination between them by providing a pulse output proportional to each particle's energy deposited in the chamber. And also it enables spectroscopy or energy measurement. So different radiation energies and different radiation types can be distinguished by analyzing the pulse height, since they significantly differ in the primary ionization. And the final one is neutron detection. Same as GM tube and IC, the inner surface must be coated with boron for particle identification. Next is advantage and disadvantages. For gigamolar, the first advantage is high amplification that produces a strong signal that improves signal to noise ratio. Next is construction simplicity, which mainly used for portable instrumentation due to their sensitivity, simple counting count, and ability to detect low-level radiation. Meanwhile, the disadvantages are that time and cannot differentiate between particles. Next is ionization chamber. The first advantage is that it uses current mode. The second advantage is the simplicity of construction that reduces costs and more portable power supplies, but still offer a reasonably accurate response. The third advantage is that it can detect neutron, and the final advantage is that it is one of the absolute dosimeter which directly measure ionization or radiation or standard dose under standard condition. And for disadvantage of ionization chamber is that it has no charge amplification. So detectors in the ionization region operate at low electric field strength, so no gas multiplication occur. And the next disadvantage is the low density. Gamma ray deposits significantly lower amount of energy into the detector than other particles. Next one is proportional counter. So the first advantage is amplification. And gaseous proportional counters usually operate in high electric field that achieve typically amplification factors about 10 to the power of 5. And the next advantage is sensitivity. the process of amplification greatly improves the signal to noise ratio of the detector. And the final advantage is that proportional counter are capable of particle identification and also energy measurement or spectroscopy. So the disadvantage of proportional counter are constant voltage, which the voltage must be kept constant when instruments are operated in the proportional region. And the final disadvantage is quenching. So quenching is actually the technique used to improve the avalanche termination.
In these slides, I'm going to discuss about when and why gas-filled dosimeters are preferred over other types in terms of their superior accuracy, wide dose range, tunable energy response, durability, and stability. Firstly, for the accuracy and precision, gas-filled dosimeters has highly accurate and precise measurement, hence less prone to errors caused by factors such as temperature and humidity. Other than that, their broad dose range makes them a true all-rounder. Whether to measure the dose in patient or the dose within a nuclear reactor, this makes them suitable for a variety of applications including medical radiation therapy, environmental monitoring, and also in nuclear safety. Furthermore, unlike other detectors with a fixed response, gas-filled dosimeters can be tailored to specific radiation energies. By carefully choosing the gas filling, they can be customized to measure various radiations, such as a detector filled with argon gas is suitable for measuring X-rays and gamma rays, while a detector filled with helium-3 gas is suitable for measuring neutrons. This makes them a versatile dosimetry option for workers who may be exposed to different types of radiation. Lastly, unlike delicate detectors that are easily affected by harsh conditions, gas-filled dosimeters can withstand the heat and radiation within a nuclear power plant or the challenging outdoor environment, making them ideal for long-term monitoring.
That's all from us. So these are references used for this presentation. Thank you for listening.